Hello guys, and welcome to this new tutorial in your YouTube channel Science and Engineering. And today we talk about Thevenins Theorem and Norton's Theorem in basic electric circuits. So we start with Thevenins Theorem. For this we have this simple DC circuit, and here we can see that we have two voltage sources here, the B2 and the B1. And we have some resistors R1 and R3, and then we have our load, which is R2. This is actually a simple circuit because it can be even much more complicated, having more voltage sources or even current sources, a mix of voltage and current sources, and even more resistors and more things. But just for simplification, we just illustrate this figure here and this example. So why do we come to Thevenin's theorem or Norton's theorem, as we'll see later? Well, the point is, if we have a complicated circuit and we need to calculate the voltage across our load, we know that the voltage across our load will always be subject to the different calculations every time we change the value of this load. So, for example, if we want to get the voltage across this load, we will need to apply the node analysis, or maybe the mesh analysis, Kirchhoff voltage law, superposition principle, since we have two voltage sources here, in order to come to the current passing through this branch or this load, and then this will give us the voltage drop and the voltage across this load. Now, if this load is changed, and it is actually something real in the reality that the load is not fixed, it's not constant, so we will need to repeat again the whole calculations. And you can imagine then, if the circuit is much more complicated, then we have to do a lot of calculations each and every time. So in order to make this simple, we wanted to put the whole thing in a simple shape like this, where we have only one voltage source, or if we are talking about Thevenin, and it's called then Thevenin voltage here, and one internal resistance for the whole circuit, which is called the R Thevenin. This is equivalent to the whole circuit resistance, excluding this load. So this will make the calculations then later easier, because then if we have this load as a variable load, changes from 2 ohms, 3 ohms, 4 ohms, it's always easy to calculate the current passing through this, and then the voltage drop across this load, since the circuit is being simplified to only one voltage source and one internal resistance. Thevenin is actually calculating the voltage across in the case of the absence of this load. So if we consider that this load is not present between these two terminals here, so it's an open circuit. If we remove this load from here, so it becomes an open circuit. When this becomes an open circuit, then this open circuit voltage, or the voltage at no load, is exactly the Thevenin voltage that we are looking for. Of course, if this circuit is ideal, then the R Thevenin, or maybe the internal resistance, might be also 0. Then in this case the voltage across the load is exactly determined by the load itself, and it is always equal to the Thevenin voltage. We'll move forward and take an example about the Thevenin calculations and how we can find it out. But before, we have to talk about some considerations about the Thevenins theorem. This theorem applies only to linear circuits, and we mean by linear circuits that the circuits that operate in a linear way. So any change in the load will cause a linear effect in the circuit. If a linear circuit is operating in a linear, in a limited linear range, and then in another range it is not linear, then it is also not considered as a linear circuit. So the whole operation range must be linear in order to consider it a linear circuit. The second thing is that this circuit must have like a one port, it must be like a one port network. So we are connecting only one load to this circuit, and we want to see what would be the open load voltage or the open circuit voltage in case this load is removed, and the equivalent resistance of this circuit, or the impedance in case we are talking about AC circuit. The next thing is actually a question of this, if this would also apply to AC circuits, this Thevenin theorem or not. Yes, of course it applies to the AC circuits as long as they are linear circuits. So capacitors and inductors are considered as also linear elements. So we can also consider this as a point of application for this theorem. For the nonlinear elements like diodes and semiconductors, we cannot include them. So we move to our example here, and we make it simple. We just have a one voltage source, because if we have two voltage sources or more, then we have to go to superposition, and then it will be more complicated. But just for the sake of explanation and making things simple, explaining just the principle of the theorem, we've just chosen one voltage source. So again, I would like to connect a load here across these two terminals, A and B, and I would like to know what would be the open load in case there is no load, or the open circuit, the no load or the open circuit voltage here across these two terminals. And in order to find out this, we can see that in this circuit, in the resistor R1, there is no current passing since there is no load here. It is an open circuit. So we can ignore this branch. So we are only left with this loop where we have the R4, R3, and R2. And the voltage exactly at this node is exactly the voltage at the point A. There is no voltage drop here, as we mentioned before. And here is our ground. So if we can get the voltage here at this point, then this is the voltage across these two resistors, the voltage drop across these two resistors, the R3 and the R2, which is the no load voltage or the open circuit voltage, which is the V Thevenin that we are looking for. For this, we can apply the voltage divider rule, which we have explained in the previous tutorial. You can see also the link here. And simply we can go for the calculations. What we want to reach in the end is a simple circuit with only a voltage source and a internal resistance, which is the Thevenin resistance. So here is the calculations. As we said that the R2 and R3, we apply the voltage divider rule. So here's the calculations, and for this thing, so R2 plus R3 divided by the sum of the resistors in the whole loop here, or the whole branch here, multiplied by the supply voltage. And if we substitute the values here, we come to the value which is 7.5. So this would be actually the volt at this node, which is actually the volt at this point A, terminal A, because there is no current passing here. There's no voltage drop across the R1 resistor here. And this would be actually our no load voltage or open circuit voltage, which is the Thevenin voltage that we wanted to find. If we move next to the calculations of the Thevenin resistance, then we just imagine that we want to look at the circuit from this side. If somebody is looking from the right to the left, what is the equivalent resistance that he would see between these two terminals if we put an ohm meter here? So in order to do that, we convert any voltage source to a short circuit, and if we have a current source, we just convert it to an open circuit. So if we convert this to a short circuit, then it becomes obvious that R2 and R3, they are both in series, and then together they are in parallel with the R4, and then the sum is in series with R1, and that gives us the total resistance in this circuit as we can see, and we come to the value 2 kilo ohms here, and here will be the calculations. As we mentioned, the R2 and R3 are in series, parallel with R4, and altogether are in series with the R1, and we come to this value. So this will be our Thevenin resistance. So now we have simplified this circuit into this very simple form. Thevenin voltage has been calculated, Thevenin resistance has been calculated. Now if we put any load here across these two terminals A and B, then it would be easily or simply possible to define or to find out the voltage across this load and also the current. This Thevenin equivalent circuit is exactly like a voltage source for us, and the R Thevenin can be seen as the internal resistance of this circuit. Next we move to Norton's theorem. It's not very much different from the Thevenin, except that in Norton's theorem we are more interested in the short circuit current across these two terminals, and not the open load or the no load, the open circuit or the no load voltage across these two resistors. So Norton will be focusing on the current. If we connect a short circuit, if we make a short circuit here across these two terminals, and Thevenin is interested about the open circuit or the no load voltage across these two terminals. So let's connect here a short circuit or a wire like this, and we try to calculate the current across these passing in this short circuit or in this wire. So as we can see here that this is possible if we first calculate the total current in the circuit coming from the supply, this one here, and then we know that this current will divide. Part of it will go into this branch, the R3 and R2, and the other part will go in the R1 and the short circuit. And by applying the current divider rule, we can find the current passing in this branch, which would be actually, if you want to find the current passing in this branch, then we just take the resistors in the opposite branch and divide them by the total resistance value of the two branches, as we can see here in the calculations. So first of all, the total voltage is the supply voltage divided by the total resistance that we see. The total resistance, what we see here, is the R2 and R3. These two things here, they are in series, and together they are in parallel with the 1 kilo ohm, the R1, and all together they are in series with these 2 kilo ohms, and this gives us the value here. Now if we apply the current divider here, we can see that the opposite branch to this short circuit is the R2 and R3, so this is the 1 kilo ohm and 1 kilo ohm divided by the total resistance of the two branches. So the first branch has a resistance of 1 kilo ohm. Here's the short circuit, and here 1 kilo ohm and 1 kilo ohm, so 1 and 1 and 1, and multiplied by the I total, then we get this value here for our current, which is the Norton current, and this is actually the current if we connect a short circuit across these two terminals. Next we need to calculate the Norton resistance. So the Norton resistance, again, if we look at this, we want to find the equivalent resistance between these two terminals. So if we look here from the right to the left, what would be the resistance across these two terminals? Again, if we have a voltage source, we convert it to a short circuit. If we have a current source, we convert it to an open circuit. So guess what? It will be exactly the same value for the of the Thevenin resistance, since we haven't changed any values here. It's the same circuit. So if we make this as a short circuit, then again the R2 and R3, they are in series. Together they are in parallel with the R4, and all together are in series with the R1, and this gives us the value, the 2 kilo ohm again, which we got before. Here is a short circuit, and then here are the calculations, and we come to the value 2 kilo ohm. As we can see, these two are in series here, added together in parallel with the R4 here, and all together are in series with the R1, so we add it here and we come to this. So what we have done now is we have simplified this circuit into a Norton current and Norton resistance, and we arrange them in this setup. So here is the current and here is the Norton resistance in parallel to its current source in this way. So we have two options. We can either convert the whole circuit into a Thevenin equivalent, or we can convert it into a Norton equivalent. This depends on the analysis which we want to do on our circuits. If we are more interested about current, then I think the Norton equivalent circuit would be more important to us. We are interested in the current in our load, which we are going to connect here across these two terminals A and B. If we are more interested in the voltage, we can convert to the Thevenin equivalent. However, we can convert from any one to the other. Actually, one remark here on this Thevenin equivalent circuit, it is actually seen, if you look here, we have like a voltage source here, and then we have like a resistance here. This is typically a voltage source, not an ideal voltage source. An ideal voltage source will only have a voltage source here, but no internal resistance. This would be 0. Okay, and then this means that the current in this circuit would be only determined by the load that we put across these two terminals. Ideal voltage source do not exist in the reality, so we always have an internal resistance as we see here. So this is a voltage source. On the other side, the Norton equivalent is seen as a current source, and also not an ideal current source, because an ideal current source will have an infinite resistance connected across to it, parallel across to it. So this R Norton should be infinity if we are talking about an ideal current source, or just an open circuit here, so an infinity. This also does not exist, so we must have a certain value here. For the ideal current source, if this does not exist, or this is infinity or open circuit, this means that the whole current will go to our load. This means that the voltage across our load is determined only by the load. So here the current is only determined by our load in case this is 0, and here the current is determined only by our load in case this is infinity or open circuit. But this does not exist, so we are talking about real current source and real voltage source, so we must have something here and we must have something here, and then we connect our load. Now if you connect the load here and we start changing the load here, we can easily get different values about this thing. Now the conversion from the Thevenin equivalent circuit to the Norton equivalent circuit and vice versa is just like a source conversion. So if we want to convert this voltage source to a current source, or if we want to convert this current source to a voltage source, we will just think of the following. If we have seen before that the Thevenin resistance and the Norton resistance, they are similar. So we have calculated this, and in our example they were both equal to 2 ohms. So 2 kilo ohms, so they are equal. So the thing here is, if this current, the Norton current here, is going like this, and all of it will go to the R Norton because here is an open circuit, then the voltage drop across this Norton resistance is R Norton multiplied by the R Norton. And this is exactly the voltage across these two terminals. But if we look here that the voltage across these two terminals is the V Thevenin, so we say that, okay, the V Thevenin is nothing but the I node multiplied by the R node, the voltage drop across this thing here. And just using Ohm's law, we can find out that the I Norton also is nothing but the V Thevenin divided by the R Thevenin. So this sums up the basic information about the Thevenins theorem and Norton's theorem, and the conversion that could be done between these two theorems. And also this conversion can be used as a checkup. So if you are asked maybe to find the equivalent Thevenin circuit for this circuit and the equivalent Norton, if we do this conversion and we come to the same result, this means that both conversions was correct, and our conversion from the normal circuit to Thevenin and to Norton was also correct. So this can be also used as a check up that we have made the correct conversion and our values are correct. I hope you enjoyed the tutorial. If you have any questions or any comments, you can just put it in the comments below. I'll be glad to answer that. Thank you, and until then